Hi, everyone. My name is James Zeng. I'm leading the AI networking software team at Meta. Thank you for joining the first Q&A section. We have speakers from the three previous talks with us live, Petr, Jongsoo, Hany, Susana, Shuqiang, and Jingyi. We've got a lot of questions from the Q&A, so let's jump right into it. So the first question is to Petr. So someone asked, why 7-to-1 oversubscription at the super spine layer was acceptable in your network? Can you talk about the oversubscription rate for different layers at your AI network? Petr?
Yeah, of course. So first of all, I believe this question is to be designed of a large cluster. First, observe that there is no oversubscription at the lower levels of a system. You would have 4 clusters connected by super spine that's oversubscribed. The rationale is very simple. When we run a large training job, like for LLM, you typically have, let's say, 4K, 8K, or 16K GPUs in one job. The traffic patterns are such that the heavy traffic remains inside these non-blocking pods or inside even the racks. The traffic that goes between these pods is data parallel, and it's much smaller in volume than what remains inside the clusters. So that justifies the oversubscription ratio to 7-to-1. I think you can even do much higher. 16-to-1 is also acceptable. 7-to-1 was very pragmatical. It was just the layout of our switches that yielded itself to have 7-to-1 ratio. But long story short, the traffic volume is much smaller because the jobs which were run were topology optimized. That's the simple answer.
Thank you, Petr. Second question to Jongsoo. The Llama 2 paper didn't really show an apple-to-apples comparison of performance difference between IB cluster and the Rocky V2 cluster at Meta, since different model sizes were trained on the two clusters. Any insights you may have into the performance difference, just accounting for IB versus Rocky? Jongsoo?
Right, so we didn't have a chance to do the exact apple-to-apple comparison in the end-to-end setting, but based on the data we have so far, they indicate they have provided similar performance, at least up to the scale we have tested. And then we expect we will have more chance to do more exact apple-to-apple comparison in the future that we can share.
Hey, thank you. So a question for Susana. In your talk, you mentioned the Gen 1 node links, which is 200 gigabytes per second, or copper DAC. Did you stay with the copper DAC for 400 gig links in Gen 2 and the node, or is it just AEC or AOC?
Thank you, James. For the Gen 2 option, at 400 gig, we stayed with copper DAC. Remember that these connections are still staying within the same rack, so AOC was really not a requirement. Also, DAC has the advantage of having no additional power requirements because it has no active equipment. So it was a more cost-effective option for our use case.
Good, thank you. Next question for Hany. Are there any similarities between the topologies of the back-end network and then the front-end network? And then do you foresee a converged model instead of running a separate back-end network just for AI networking?
Thanks, James. For the first part of the question, yes, both network topologies of the back end and the front end are based on the claw architecture, in which the leaf switches connect to the servers and the spine switches interconnect the leaves in a full mesh. The back-end network is constructed as a two-stage claw topology. However, the front end has more stages than the back end as it connects to the backbone. So that's for the similarities between the two networks. Now, for the second part of the question about foreseeing a converged network for AI networking. So currently, we are finding value in having the two networks separate, as we are able to upgrade both networks independently. The technology path in the back-end network appears faster than the front ends, having a separate back-end network allows us to move to faster speeds. However, we are definitely learning through this great journey of building infrastructure for AI, and perhaps at some point a converged network, the thought of a converged network may resurface as an option in the future.
Okay, thank you, Hany. So next question is about the FHT routing in general. Maybe Shuqiang, you can answer this. How is DPR different from source and destination packet hashing? And then how do you generally, how do you compare traffic engineering with other ways of load balancing, such as packet spraying, dynamic load balancing, or adaptive routing?
So I will answer the first part of the question first. So how is DPR different from the source and destination hashing? So our DPR is actually solely based on destination. So it's actually based on the destination index. So it's not actually hashing on each packet based on the 5 tuples. About the second part of the question, I think, how do we compare traffic engineering with packet spraying, those kind of technologies? I think they both have pros and cons, and it really depends on the workload. So traffic engineering is especially suitable for the workloads that are predictable, deterministic, and has actually big elephant flows, which happens to be the current characteristic of our current AI workloads. And I think one advantage of traffic engineering is that you can have the deep visibilities into where your packets are routed, and it's also more software driven, so it's quick to iterate. But one challenge for traffic engineering is that it has relatively coarser granularity of flows, so it imposes a higher requirement on the optimality of the path allocation algorithms. In contrast, I think packet spraying technologies, it has control over like more fine-grained flow nets, and it can be actually more adaptive to unpredictable workloads. But you might not actually need to maintain a centralized control plane there, and it can be a challenge to tune its parameters, and also it needs actually more resources and also intelligence at the hardware layer. So it might be slower to iterate. So overall, I think it's possible for us to combine and utilize the pros of both technologies, and we'll actively explore the chances there.
Okay, thank you, Shuqiang. Question for Jingyi. So on the FHT controller, we all know that the AI training models are changing at a rapid pace. So the question is that if traffic pattern in those models change over time, is the traffic engineering solution still going to adapt to it?
Thank you, James. I think the key to the question is identifying the logical topologies used by collectives. And that's how we can continue to adapt to the new patterns we discovered. So this can be done in a reactive way or a proactive way. So as mentioned in the talk, the current approach we are taking is to collect traffic patterns or traffic matrix from the network, which is more the reactive route. This helps us to identify the elephant flows, and it is especially beneficial for collectives that have coarser flows, such as our reducer or gather that are using the ring algorithm. There will be a delay in the TE reaction time, but considering the workload typically lasts very long, this is less of a concern in our current AI clusters. Now, the proactive way, on the other hand, can be very interesting, as we can explore getting this logical topology information either from the application layer or from the collective layer. The trade-off here will be a more complexity in the operational time.
Hey, thank you. So next question, maybe for Petr. Meta does not appear to be using NVIDIA's recommended rail optimized design. Is it just not required, and is there any like custom nickel optimization to be used at Meta to accommodate it? Maybe you can share some learnings in this regard.
Yeah, thanks, James. I guess it's in reference to the clusters we have shown. To be clear, the design we presented is only one instance of things we build. We do have different topologies with InfiniBand, which wasn't discussed yet. But in the majority of cases, for the clusters we built for ranking jobs training, we do use Tor architecture indeed. What we found out is that topologies like optimized design offer some benefits like latency reduction in the first stage and simplify offload for the collective in the network, but that wasn't critical for the ranking workloads we are running. For instance, in ranking training, we overlap or reduce and backward pass through real compute. So it wasn't exposed that much. And all-to-all traffic doesn't benefit much from the real optimized. And top-of-rack design simplifies deployments a lot. You have a rack switch in your rack, so it's much easier to roll in production. So this was our first design, first choice 3 years ago, and we stuck with it for some of the deployments. But as I mentioned, some of our designs do use optimized topologies. This is where latency does matter. As for nickel and optimizations, we don't have any specific tricks that we use internally. We use open source version. Everything we do, we contribute to open source. For instance, the all-to-all implementation in nickel came initially per Metis request, and everything else we do also open source with NVIDIA together. Thank you.
Cool. Next question is for Shuqiang. Someone asked that the controller to compute new topology and download new forwarding states. What is the protocol used between the controller and then the nodes? How do we download the states?
So we do have actually streaming protocols through Swift to upload and download states between controller and network nodes.
Okay. Next question for Jongsoo. You talk about the AI workload like we use in Meta. Are those AI workload running in VM, virtual machine, or bare metal on hosts? Does those workload running in the virtual network separate from the physical network? Can you talk about whether we use any kind of virtualization technology at Meta?
Yeah, so we use a technology called Tupperware. It's not the exactly same kind of VM technologies out there, but we use a Tupperware.
Okay, thank you. Next question from maybe for Susana. From a physical infrastructure perspective, what are the main lessons that we learned after completing this design?
I think one of the things that I started thinking after we completed the first iterations of the design is like you spend years designing data centers for like a specific purpose, right? In our case, we were supporting regular OCP servers that need to connect to our regular data center fabric, and it's kind of like a repetitive requirement that was static and was not changing much. When you start doing that, then you start thinking about optimizations, right? Like how do we improve and make this deployment faster, simpler? From a cabling perspective, right? Like how can you reduce the amount of cables that you have to run? How can you make it simpler? Maybe you build a customized solution for like interconnecting your servers or the layers of your network or between the rooms in the data center. When the requirements change, like in the case of like AI brings a new requirement to our data centers, all these customizations, right, like puts us in a kind of like a corner or like a special place because you lose kind of like the flexibility that you need to support a new use case. And I think it's not like specific, like something very specific, but more like a general engineering thing. You want to over customize, you have to lose some of the flexibility that you need if you want to move fast or like if you want to change the requirements. So I think that was one of the main things that I noticed with the physical design.
Hey, thank you. Maybe I have a question for Jingyi, which is talking about the link failure. In the case of link failure, the traffic engineering, your controller will fall back to the traditional routing, which is BGP. Do you experience any kind of increase in latency, which would be pretty bad in a rocky network? If yes, how do you prepare to handle these events?
Yeah, thank you. So we did some benchmark using the actual workload in the AI clusters. We see slight latency increase when it fall back to BGP, but we don't typically see queue build up in the switches. Our SLA is basically the controller will come back in 30 seconds to update the forwarding table so that it re-optimize the traffic in the network to avoid this kind of congestions. Within these 30 seconds, we see the latency increase, but we don't actually deal. Well, it's not like as critical as queue build up, or we actually lost a connection between the collectives. So we just live with it for a short time period.
Thank you. Next question for Hany. How are the service job provisioning methods handling different ports or regions with variance in latency, especially when you onboard new fabric capacity, that's a 400 gig interconnect versus old fabric, which is having 200 gig interconnects?
Thanks, James. So we do have an internal system that we developed in-house to do the scheduling of jobs, training workloads, based on certain properties and requirements for that particular job. So it does take into account what sensitivity the job requires, and that includes latency parameters. And based on these requirements, the system decides the best fit environment to place that job and over how many GPUs. And in what kind of data center build, right? So we actually take that into account when placing workloads by examining the properties and the requirements of the job that we intend to run.
Thank you. Maybe next question for Jongsoo, which is like more future looking. Like you talk about like running very large models, and then when do you expect that we see clusters has like 64,000 or even like 100,000 GPUs if a job size keep growing?
Yeah, thanks, James. So predicting the future in AI is really, really hard. So the short answer is we don't know yet. But we need to be prepared in terms of the technologies and then design, so that when we actually need that large cluster, we should be able to deploy it. But one thing I wanted to point out is kind of exponential growth of the size of cluster is also not sustainable. So we need to invest a lot on the efficiency technologies to bend the curve.
Okay. Thank you. Maybe another question for Petr. What do you think is the most important property for AI fabric? What do you consider when you design a new AI fabric?
Oh, must be my lucky day, James. All those questions. So funny enough, the most important property is buildability. Will you have materials on time to build your fabric? I know it's controversial, it's very unusual to say this thing, but what we found out is that building a large system requires you to get a lot of components in time in one place and test them. So from that perspective, you have Ethernet and InfiniBand as two poles that can solve the same problem in different ways. Ethernet offers you an open ecosystem, multiple vendors, and easier supply sources to get your hardware. InfiniBand offers you pedigree of the technology used in HPC clusters, but only one suppliers as of today. So the question is, whatever is most important part for this fabric, and I say whatever you can make work on time you need. So for us, for the longest time, it was Ethernet. We began with Ethernet like early on. we built many fabrics on internet because this is technology we're familiar with. We had supply relationship, we have devices to deploy on time, and that took precedence. Recently, we've been building fair cluster with InfiniBand as far as like a few years ago. So we always expanded our technologies. So as of today, we're learning to deploy both InfiniBand and internet. And once again, I'll reiterate, the most important property is building the fabric you can build on time for your GPUs to arrive and use in your data center. Thanks, James.
Thank you. Maybe next question is a slightly technical questions for Jingyi. How does the TE solutions deal with the network partitioning?
So I think in the first place, with the class topology design, we really see a network partitioning case happen. But in traffic engineering solution, in case that actually happens, we don't really have a special handling. This is more about same thing as a link failure or node failures in the network. We do, however, have pre-flight checks before workload starts, and that should detect this connectivity outage between the GPUs, and then it's up to the job scheduler to either reschedule the job into a different set of GPUs.
Cool. Let's conclude with the this Q&A section with last question to Jongsoo. Talking about the AI workload. So what are the biggest challenges when working with the Gen AI training and inference, which is obviously a very hot topic nowadays?
Yes, thanks, James. So the biggest challenge is AI is moving so fast, so it's hard to predict what the future workload will look like versus system design needs some time. So that's the first challenge. And the second one is, especially when you are running large language model, then there are so many components involved. So when there's a failure or slowdown, it's very hard to attribute where the issues are coming from. So that's another challenge.
Cool. Thank you, everyone. That concludes our Q&A section. Let's thank speakers again. And then we will be back after a very short break. Thank you.